in the last class, we looked at the notions of what we need to worry about while working with single supply as well as what to watch out for when you choose a coupling capacitor. So today we will look at some more applications of some basic op-amp circuits. And before that, let's see what all we know about the op-amp already. So ideally, of course, VO must be equal to some A times V1 minus V2, where A tends to infinity. This is the very basic model that we used. Then we said that, well, the output voltage cannot right. So, the output voltage cannot exceed the upper rail and cannot go below the lower rail of the supply voltage. Then we added another constraint, and namely that V1 plus V2 by 2 must be in the common mode range of the op-amp. In other words, I mean we know that once the op-amp is embedded inside a negative feedback loop, the nodes V1 and V2 will be very close to each other, right. But that only happens when the op-amp's gain is very large, and that gain will not be very large unless the common mode of the input of the two input nodes lies within a common mode range at the input of the input stage of the op-amp, and in general the common mode range will only be a subset of the supply range, right. It is of course possible to specially design op-amps where the common mode range can be the same as the supply range or sometimes even larger than the supply range, but in general the common mode range will basically be a subset of the supply range. Now, we will add more non-idealities today. So, one common when one non-ideality is the following, it is called offset. So, ideally VO is A times V1 minus V2. In reality, VO is going to be A times V1 minus V2 minus some offset voltage V off. Okay. So, all that it means is that, so this is what is called the offset voltage. So, the if I plot the input output characteristic of the op-amp, this is V1 minus V2 and this is VO. Of course, this is in a suitably small scale, right, so that we can actually see some slope here. So, say that is VDD and this is VSS. So, this is the ideal one. So, the flat region is because of saturation of the op amp. So, this is due to saturation, this is because of saturation, all right. And but in reality what happens is that, well, there is the characteristic is moved to the right like this, and that is V offset. Okay. So, when the input is ideally we think that when you short the two inputs of the op amp, the output should be ideally, if you short the two inputs of the op amp, what would we expect the output to be? Ideally, when you short V1 with V2, what do we expect the output to be? 0, right. In reality, what will it be? At least from this picture, it seems like it will be some A times V offset, and if V offset is sufficiently large, right, then what do you think will happen? It will either be plus VDD or minus VDD, right. So, so if that gain A becomes is very large, or the offset, if A times V offset is larger than VDD or smaller than smaller than VSS, then the output of the op amp will be, when you short the two inputs, will be saturated to one or the other rails. Okay. And how do you model op amp offset in the schematic in the equivalent circuit? So, well, earlier we had so this is offset. A times V1 minus V2 minus. All right. So, now the question is, what does it do to, once you have offset, what happens to most of our common circuits that we build. Okay, let us take a few examples. So, let us take our so what is the effect of so what will the output be? How will we solve this problem? I mean, this is the op amp. It's now got equivalently, it's got an input voltage source in series with one of the terminals. Okay, so what is the output? I mean, how do we go about finding what the output voltage is? Yeah, so basically the solving when there is offset, it's actually pretty straightforward. What do we do? Well, the part after the offset still behaves like an ideal op amp. So, that voltage is going to be 0, correct. So, if this is V I, what is the potential there? V I minus V offset. What is this voltage? V I minus V offset. And so, basically you can think of the input as being V I minus V offset rather than V I, and the rest of the circuit is you have seen it already. So, V O is simply V I times m plus 1 times V I minus m plus 1 times V offset. Does that make sense? Okay. So, there is really, I mean, it's, you just treat this as another independent source, and then analyze it like we did before. If you like to use superposition, that is also fine, right, but that is all there is to it. Let us take another example. Again, I mean, so offset in the op amp reflects as offset in this closed loop amplifier, right. So, ideally in the closed loop amplifier, when you set V I equal to 0, we were expecting the output to be 0. Now, what are we seeing? What will we see in the at the output? When Vi is 0, you will see minus m plus 1 times V offset. Okay. Let us take another example. Let us take, and by the way, when I draw circuits like this, what comment can we make about the supply? Is it a single rail or dual rail? We are assuming that we are working with positive and negative supplies, okay, because this is grounded. You understand, right? If you want to work this off of a single supply, then this the other terminal of the resistor R would be connected to VDD by 2 or analog ground. Is that clear? All right. Now, let us take another example. So, this is R and this is M times R, this is V I. Ideally, of course, there should be no offset in the op amp, but in reality there is. So, basically all right. So, what comment can you make? What is this voltage? The difference here must be 0. What is this voltage? Minus V offset. What is this voltage? That will also be minus V offset. So, what comment can we make about the output voltage? I mean, you can use superposition if you want, right. So, if you assume V offset is 0, what is the output voltage? Minus m times V I. If you assume V I is 0, what is the gain from the offset to the output? Minus of m plus 1 times V offset. Does that make sense? All right. So, I mean, so like before, the rules, I mean, adding this offset is not going to change the polarity of the feedback, correct. So, as long as the op amp is in negative feedback, the offset just is like one more independent source inside the circuit, and you can simply use the standard techniques of network analysis to go and find the output of the of the amplifier is, right. It will have one term corresponding to the offset, it will have one term corresponding to the input. So, in general you will basically find that when you set the input to 0, you will have some offset at the output. So, in some cases this is a problem, in which case people do something to correct it. Most of the time the amplifier is typically, the output of the amplifier is typically being digitized later, right. So, what one thing you can do is you set the input to 0, measure the digital code that is coming out at the end of the signal chain, right, store that, and then when you apply the real signal, you can subtract off that digital code from the from whatever digital code you get. Basically, this is called digital correction of offset, right. So, in many cases the offset is not problematic, in which case you do not bother about it, as long as it is not too large that it causes saturation elsewhere.